Hello, hello. Maybe we can talk about this a little here. Maybe we can talk about this here. We need that space. Need some more space here. All right, 9 p.m. Let's get started. Hello, everybody. Good evening. I am Layman. I will be running through acid and base titration calculation questions today for your upcoming HSC, which is Friday. Wishing you guys best of luck. If you guys haven't started studying already, I think it's a good time to start, but I'm sure you guys are on top of it. Let's get started on these questions. So I guess I want to touch on a little bit of theory, but hopefully I'll get through that along the way. The concept of these questions, the purpose of these questions, again, how does this relate? You know, to you it might seem like a very easy, or it might seem like a calculation to you guys, but there's actually good uses for it. As you guys can see from these questions, hopefully you guys have done enough to know that these are typically used to find unknown concentrations of certain things. It's also used to find, just to confirm the concentrations of certain things as well. So a very big aspect of that in industry. So let's get on to it. So what does a typical acid and base reaction incur? So, we've got our acid, we've got our base, and that gives us some sort of salt plus water, right? You guys should know that one. Let's start with this question. Now, the references of these questions are towards the bottom. So this one's from Ashcam Year 12, 2019, question 8, multiple choice. Now, these multiple choice are very long. They're not worth the 1 mark, but it's very satisfying after you can get the answer. Okay, so let's get started. A student wanted to determine the percentage of magnesium hydroxide in a 1.24 gram antacid tablet. The antacid tablet was added to 50 mils of 0.1 mole per liter hydrochloric acid. The excess hydrochloric acid required 20.8 mils of 0.1133 moles per liter NaOH for neutralization. Calculate the percentage by mass of magnesium hydroxide in the 1.24 antacid tablet. Okay, great. Let's start with our equation first. Always start with our equation. So that's MgOH bracket 2 aqueous. Now that's the material that's going to be reacting with our hydrochloric acid, and that salt is magnesium chloride, aqueous, and also water. Cool. Now balancing. Mg's are balanced. Let's balance our Cl. Cl is 2. We've got 2 there. Is that balanced? We've got 2 hydrogens on the left. Sorry, we've got 4 hydrogens on the left. So we need 2 there. All right, I think that's it. Now, as you guys can see, this question has 2 titrations. So there's this titration first. I'll denote with 1. And then there's the second titration, which is HCl aqueous plus NaOH aqueous gives you NaCl aqueous plus H2O. Now, this is your very standardized HCl plus NaOH neutralization reaction. So what this question is saying, we have reaction 1 happening in excess acid. Now this excess acid comes to here and gets reacted and gets titrated, with your NaOH. So if we can find the excess of this, we can find out the initial, which is numbers from the question, and then we can deduct the initial, the excess from your initial to see how much was actually consumed. Okay, so let's see to work that out. Okay, so let's work out the excess first from our numbers of our second titration, which starts here. Okay, this is our second titration. Now it's very important to read and to understand what section it is. Now this is a multiple choice. We're going to get into harder questions, of course. So hopefully you guys will know how to interpret these by doing a lot of these as practice. So our second equation, we do, what can we work out from that? We got the excess hydrochloric acid requires 20.8 mils of 0.1133 moles per liter NaOH. So we can work out our NaOH moles, so that's 0.0208 liters times 0.1133 moles per liter. Now what does that become? That gives us, now I like to write in scientific notations as opposed to writing all the zeros, especially when there's a lot of zeros. So that's that many moles. Now we can say the N of HCl, I'll just denote this one as excess, but this is all in reaction 2, right? Reaction 2, excess is equal to the same, which is equal to NaOH moles. Reason why is because we've got our 1:1 molar ratio. So we just say that, and we say 1:1 molar ratio with our NaOH, as you can see from this equation, number 2. Cool. So we got our excess, beautiful. Let's try to find our initial HCl that we use for equation 1. So for reaction 1, the N of HCl initial equals to 50 mils, 0.05 liters times 0.1 moles per liter, which gives us, in scientific notation, that is 5 times 10 to the negative 3 moles. Okay, now we can look at the excess minus initial, which will give us how much is actually consumed in reaction 1, right? So N of HCl consumed is equal to 5 times 10 to the negative 3 moles. I do want to mention, guys, sorry, I didn't mention this at the start, but down in the description, there's a link to the questions that I'm working on. So feel free to click on that and download that PDF document and work as I go, or you guys can do this whenever as practice, but you guys can have this video as a reference for you guys. So let's continue. We minus that to get how much was actually consumed. So we do 5 minus that number. Now, as a tip for my students, typically I like to say, write out your calculator value to about 5 or 6 significant figures. Now, the reason why you do this is because if you lose your calculator value, let's say you work this out and then this out, you've got enough digits for you to work out the number and then use those numbers, significant digits, to carry on your working out. If you round it off too early, you're going to have an incorrect answer, because these digits, let's say you've rounded off to 2 dB, these digits gets lost when you decide to round off early. So it's very important you carry the full number as far as you can up until the very last point. Okay, so we've got our moles of HCl consumed. What do we need to find next, right? We need to find ultimately the moles of magnesium hydroxide so we can find the mass. So how do we convert the moles of HCl that was reacted in this reaction to the moles of Mg bracket OH2? So we need to look at the molar ratio. Okay, so how I like to look at this is very simple. Okay, I like to put it as a fraction. So I say HCl consumed over moles of MgOH2 is, what are the coefficients of this reaction? So based on the coefficients, I write the coefficient of the HCl over the coefficient of Mg. All right, so in order to find Mg, I can move that upwards and I can move the 2 downwards. Okay, so what does that mean? The moles of MgOH2 is equal to half of the moles of HCl consumed. And that equals to half of that number, moles, which is 1.32168 times 10 to the negative 3. Cool, so that's the moles. How do I get the mass? Okay, two more steps, bear with me. The long multiple choice, as I said at the start. Mass MgOH2 is equal to moles times molar mass, which is 1.32168 times 10 to the negative 3 moles, times the molar mass of MgOH2 is 24.31 plus 2 times 16 plus 1.008. For those who just joined us, welcome. If you guys have any questions, feel free to pop it in the chat. There's a link to these questions in the description below, so feel free to join. Click on those, work these out with me as we go. Hopefully you guys won't have any questions, but if you do, I'm here to help, so send them my way. Okay, so I'm popping these into the calculator. We get 0.077088 moles. Oh, sorry, not moles. It's grams. And then to work out our percentage weight by weight, we do the mass of MgOH2, over our mass of our antacid, sorry, 0.07088 over the initial mass of antacid is 1.24 grams, so that's 1.24 grams times 100%, which is over 0.06, sorry, it's a percentage, isn't it? 6.216 ... which is answer closest C. Done. I know there's a lot of working out for this one question, but I'm just trying to show you all the little steps. I like to go over beyond, just in case I get it wrong, you know, I can track back. But At your discretion. Hopefully that helped this question. Let's move on to the next question. 29. A 25 ml aliquot of sodium carbonate is to be titrated with 1 molar hydrochloric acid solution. What mass of dried anhydrous sodium carbonate must be dissolved in 250 ml of deionized water so that the 25 ml aliquot of sodium carbonate solution will need a 20 ml titration of hydrochloric acid? All right, there's a lot of words, a lot of numbers, might be a little bit confusing, but essentially you want to have some Na2CO3 solid dissolved in a beaker and a conical flask with 250 mils. And then I want to, after that's been dissolved, I want to take 25 mils of this solution and I want to titrate it with 20 mils of HCl, 1 molar. So let's write a chemical reaction first, as the question has suggested. Because it's a solution, we're going to work in this direction. Cool. We're going to do this titration and then work backwards for dilution. Okay. So Na2CO3 plus HCl aqueous gives me. So this one's slightly different. It's an acid plus metal carbonate, which gives us our salt, CO2, and H2O. So our salt here is jumping steps, NaCl aqueous plus H2O liquid plus CO2 gas. I need to balance this, balance that. Is it balanced? Yes, perfect. Let's move on. So from this question we can find, first of all, the initial concentration of HCl, or the HCl that we use for titration, right? So HCl, moles is equal to C times V. That's on the data sheet. C is 1 molar, or 1 mole per liter, times 20 mils, which is 0.02 liters. And that's just 0.02 moles per, just moles. Now, we use our molar ratios to find what the mole of sodium carbonate will be. So the moles of sodium carbonate would be so we can use our little fraction again. So the ratios, the coefficients in front of these guys are 1 to 2. So that means N of Na2CO3 is equal to half of moles of HCl, okay, which is 0.01 moles. Cool. So we've got the moles of our Na2CO3 and we need a concentration, okay? The reason why we need a concentration is because we need to know how many moles of Na2CO3 is required to be dissolved in the 250 mils. So we need to find the concentration of this first, and that'll be the concentration of this. Okay, so we need to find the concentration, so you can denote the concentration by the square brackets of whatever's inside by moles over volume. So 0.01 moles over the volume. In this case, for the titration, this is for titration. This is the volume of titration, which is 0.025 moles. Cool. So, what is that? 0.01 over 0.25, 0.4 mole per liter. So that is the concentration of the aliquot of the sodium carbonate solution that was diluted. So we've got a concentration, we've got a volume that we want to previously achieve. So this 25 mils was taken from 250 mils. So if I take 250 mils of, if I take 25 mils of this solution, regardless of how much I take, the concentration is still going to be the same. Okay, so the concentration being the same, I do C equals to N over V. I want to solve for N, the N of Na2CO3 for specifically for my solid, right? So what is that? That's just C times V, which is 0.4 times our volume of our initial volume that we diluted it to, which is 250 moles per, oh, not moles per liter, just 0.4 moles per liter times 0.25 liters. So what does that become? 0.1 moles. Cool. Now this is our moles of our Na2CO3 solid. How do we get a mass of how much to add in there? So we do this through moles times mole mass. The mass of Na2CO3 solid, Na2CO3 solid, times by the molar mass. Now what's our molar mass? So this will be 0.1 moles times 22.99 times 2 plus 12.01 times, plus 3 times 12.01. Oh, did I do that twice? Yes, I did. 16, which is equal to times 2, 3 times 16, 10.599 grams. Now, we always end with two things. We always end with the number, the number rounded to the nearest, to the lowest number of sig figs. So how many sig figs did we use? The lowest we used 2 sig figs. So this is 11, and we always have units, and we always have the number of sig figs we rounded it off to. So it's 11 grams 2 sig fig. Cool. Yes, so it's important to map out to understand what the question's asking for, how many different stages there are, what numbers correspond to which stage. Yes, so hopefully that is clear. If there's anything not clear, please leave a comment in the description below. Happy to answer any questions you guys have here. Cool. All right, so let's keep going. Oh. Alright, it's gonna lag. That's fine. Okay, an antacid contains some magnesium oxide. Magnesium oxide. Okay. Oh, not helpful. Okay, let's leave that. Antacid contains magnesium oxide. 40.6 grams of antacid was dissolved in 500 ml water, then diluted to 1 liter. A 100 ml aliquot was then removed and reacted with 100 ml of 2 moles per liter hydrochloric acid. The excess acid required 19.7 ml of 0.2 moles per liter sodium hydroxide for neutralization. What is the percentage of magnesium oxide in the antacid table? Okay, great. Let's start with our two reactions. So our first reaction is MgO. Does it say what it is? It was first dissolved. So we assume this will be aqueous, HCl. What does that give us? MgCl2 aqueous plus H2O liquid. MgO balancing 2 there, 2 there. Okay, that's our first reaction. Our first reaction goes to there. That's number 1. The excess acid required 19.7 ml of that. That's our second reaction. Aqueous, NaCl aqueous plus H2O liquid. That's our second reaction. Now we can use this number to find N of NaOH, which will N of NaOH, which is 0.0197 times 0.2, which is 0.003. Let's switch that to scientific notation. Moles, and we know that's the same as what's being excessed, because 1-to-1 ratio, 1-to-1 molar ratio. Okay, So let's find the initial HCl that we used, which is 100 mils of 2 molar. 100 mils times 2 moles per liter, which is 0.2 moles. Is that right? Yep. So our HCl consumed is just HCl initial minus HCl excess. Now, yes, by all means, you don't need all this working out. You can, if you have the time. If you don't have the time, just do a rough working out, because these questions are probably the ones that's going to take a lot more time. It's not very easy to just see the answers. You need to spend some time working out these answers. Okay, and we can then do our molar ratio between our N of HCl consume, which is our first reaction now, and of MgO, which is 1 to 2. Oh, sorry, not 1 to 2, 2 to 1. 2 to 1. So we can say N of MgO is equal to half of NHCl consumed, which is 0.09803 moles. Now we need the percentage mass, which is mass of MgO times the molar mass, 3.95. Did I did, yes, yes. So, jumping back, I have left a stage. So there is a reaction, but then there's a dilution. So, which I forgot. MgO, that's the diluted, right? So we're up to there, we're at this point, right? So it was only 100 mils aliquot. Yeah, so this is saying that in 100 mils, I have this many moles. So if I had 1000 mils, which is 1 liter, how many moles of this do I have? Well, it's simple. If I have 100 mils of this particular number of moles, then I would have 10 times that. Okay, now the concentration is going to still stay the same, but the number of moles is going to be 10 times. So if I have 10 times that, oops, that's going to be 0.9803 moles, which is our initial diluted amount. Okay, so it doesn't matter. I don't need to work out concentration anymore because I've got the moles in my 1 liter, and that 1 liter is also the number of moles which my antacid was originally dissolved in. So I don't need to work out anything concentration related. I just need to work out the moles, which is that. Now I can just work out the mass, which is moles times molar mass, which is 0.983 moles times 24.31 plus 16. Cool. So 16, oops, that should equal 39.51589 ... And then to get our percentage mass, we do 39.515893 ... over our initial mass of antacid, which is 40.6, which is Ooh. It's about 97.3297 ... which to our multiple choice answer, it is D. Okay. Now, cool. Let's do question 8. In titration, a 25 ml titer of 1 mole per liter hydrochloric acid neutralized a 20 ml aliquot of sodium hydroxide, which was in a conical flask. In repeating the titration, the titer would be, okay, now you're given a lot of options with different scenarios, okay? So the confusing bit is to know what to wash what with, okay? Now, it's a bit of revision. We want to wash everything. Wash all with deionized water. So this is your pipette, this is your burette, and this is your conical flask. All right, now we follow the washing of the deionized water with the type of solution that they're going to be transporting. Okay, so we look at this as type of solution transporting. Okay, so we want to do pipette. Now, depending if you're using your titer as an acid or your as your titer of as your base. So I'm going to say we're going to have the burette containing, as in the titer, it's going to have acid, and my conical flask is going to have a base. Okay, so I'm going to use my pipette to transfer the base into the conical flask. Because I'm transporting it, I need to wash it with that particular solution. So I need to wash the pipette with our base, and then I need to wash our acid in our burette. Okay, because we're transporting, we want the exact amount of moles in there. That's why we rinse. For example, the conical flask, we're not transporting anything with the conical flask. The conical flask is the end, the destination of the titration, of the titer. Okay, so for this conical flask, we don't rinse with any solution. We don't want to add any other moles of acid or base into this. So after the conical flask is washed with deionized water, forgot to specify 3 times, then we don't rinse the conical flask any further. Okay, so we've got a titration, 25 mils of our acid, 1 mole with 20 mils of the sodium hydroxide. In repeating the titration, the titer would be, so the titer should be the same if we've washed this the same way. Okay, let's go through our options. Equal to 25 mils if the water was left in the conical flask after final rinsing. Okay, yeah, that sounds right, because we don't want to rinse the conical flask with anything else but the water. So let's just leave a tick there for now. Less than 25 mils. Okay, we can have less than 25 mils if for some reason we've decided to add more base into our conical flask, which will result us we've decided to dilute the burette. Let's say we don't rinse the burette with acid. Then, if we decide to rinse the conical flask with the acid, then we'll incorporate more acid into the conical flask and hence require less of the titer. Hope that was not too confusing. Less than 25 mils if the final rinsing of the burette was with water rather than the acid. Okay, so if we rinse that with water, it would dilute the burette, and by diluting the burette, we would need more volume, so that's not correct. Greater than 25 mils if the final rinsing of the 20 ml pipette was with water rather than the base. Okay, with the final rinsing of the pipette with the base. Okay, in this particular situation, I actually should have known this, should have written this down. But they're saying 25 ml titer of a 1 mole per liter hydrochloric acid neutralized a 20 ml aliquot. Okay, these words are very important. Okay, titer and aliquot. What do they mean? They indicate where each solution are. So for our titer, this will be in the burette. Okay, it matches with what I've written. I knew that. And the aliquot is what we put in the conical flask. So if we rinsing the pipette with the base, okay, that's true. First of all, we do. If the final rinsing of the 20 ml pipette was with water rather than the base, okay, so we would then dilute the base. So dilute base, as in we end up having less moles base in conical flask. So what's the result of that? Then we would need less acid. So our titer will be less than 25 mils, not greater. So that's not true either. D, greater than 25 mils if the conical flask was rinsed with acid prior to the addition of the aliquot. Okay, so we've got our base in our acid. So by adding acid in there, we're going to neutralize some of that base. What that means is we're going to have less moles of base. And what's that going to do? That's going to give us a smaller titer. So that's not true either, because this should be less. Okay, so our option is A. Hope that makes sense. The washing, when you're doing a procedure, if you do get a question like that, be sure to specify a repeatable experiment, aka list how many times you want to rinse your solution, rinse your equipment. Okay, specify. It needs to be repeatable. Okay, washing with deionized water, does that mean 1 time? Does that mean 2 times? Okay. Question 17. Using the same 0.1 mole per liter hydrochloric acid solution, a student carried out 2 titrations. Titration 1, sodium hydroxide, same volume, same concentration as titration 2, ammonium solution. Okay, so what titration counterparts are there? Okay, so with hydrochloric acid, sodium hydroxide, we have a strong acid, strong base. For hydrochloric acid and ammonia, we've got strong acid and weak base. So we know our combination of strong acid, strong base gives us a salt, which is neutral being pH 7, and our strong acid, weak base gives us a salt, which is acidic, which means a pH less than 7. Okay, so just looking on the pH for the equivalence point, we want to see that the titration 1 should give us a pH of 7, and titration 2 should give us a pH less than 7. So what is that? Where is that the case? The case is here, D. Now, the volume of hydrochloric acid required to reach equivalence point. Now, why are they the same? One's strong, one's weak. Surely one's going to be different, right? You think. But it's not. Now we've got our strong acid here. It does the usual thing that we typically know of, that it does, creates NaCl. Now, the beauty of a weak acid is, a weak base is this. Okay, I'm not going to draw the neutralization reaction, but rather I'll show you these equilibrium. Oh. Can fix. Okay, now as I add more HCl, I react with this guy, right? Or namely, not HCl. If I have H plus, I react with this guy and I form water. That's our neutralization reaction, correct? Now, based on our understanding of Le Chatelier's principle, which states when a change occurs in a system, the system will shift to oppose it. So by having this, we're going to keep shifting this way, right? By having our H plus attacking our OH, reacting that with water, we're going to keep shifting it to the right. So what will happen to our concentration of our NH3? It's going to eventually get consumed and be converted all into our NH4. So what that means is, over time, you're still going to require the same number of acid volume or molecules in order to have a complete reaction. So the volume is going to be the same regardless of a strong or weak acid. Okay, so this is how you explain it. You explain this in an equilibrium system, that the OH is getting consumed and you're shifting right due to Le Chatelier's principle. And over time, your base or your acid, whatever the case is, the weak aspect of that will shift it all to the right and convert all your weak acid, in this case weak base, to your conjugate acid. Okay. All right. I want to do a harder question. I want to jump to a HSC question, which is 32. So, 32. The concentration of citric acid or triprotic acid, okay, very important, triprotic. What does that mean? Proticity means how many protons does it have? Okay, triprotic means 3, so it has 3 hydrogens available to give out. Now, this gets confusing in terms of the strength of it. You don't need to worry about that. All you need to know is it reacts in a ratio, certain ratio, with 3 hydrogens here. Okay, so this will come into handy when we do the reaction with the citric acid. Okay, step 1, a solution of NaOH solution was standardized by titrating it against 25 mL of aliquots of a solution of monoprotic acid, potassium hydrogen phthalate, KHP. The KHP solution was produced by dissolving 4.989 grams in enough water to make 100 mL of solution. The molar mass of KHP is 204.22 grams per mole. The results of the standardization titration are given in the table. Step 2. A 75 ml bottle of drink was opened. The contents quantitatively transferred to a beaker. The soft drink was gently heated to remove CO2. Step 3. The cool drink was quantitatively transferred to a 250 ml volumetric flask and distilled water was added up to the mark. Step 4. 25 ml sample of the solution was titrated with a NaOH solution. The average volume of NaOH was 13.10. Okay, again, we've got 2 titrations here. We've got titration 1 here, and then we have a dilution stage, okay, which will be important here, and then we got a titration number 2. Now, from the looks of things, we need to first work out the concentration of NaOH from titration 1, and then use the known concentration of NaOH to work out our unknown concentration of citric acid. So, how do we do that? So, monoprotic. Okay, let's circle that as well. That will be very helpful. Monoprotic acid reacting with NaOH. So let's write a equation. Let's write KHP solution plus NaOH solution gives you NaKP plus H2. Now you might not know what the formula is. Don't stress. Just write that and just imagine this is the chemical formula of it. It should be, and then might not be actually. The phthalate might look a little bit slightly different with some O's in it. Just take it out. Just do an equation like this. That'll be fine for a marker. Okay. You know the key thing is to know the 1-to-1 ratio, right? So we can say we'll use that later. Okay. So we need to find the concentration of our KHP first, or at least the moles of KHP. So how do we do that? N of KHP. Oh, why am I writing mistakes in there? KHP equals 2. We got a mass. We got a molar mass. Lovely. 4.989 over 204.22, which is 204.22. 0.0244295 ... moles. Now our molar ratio between our KHP and our NaOH is 1-to-1. KHP is monoprotic. So monoprotic in this case just means 1 proton available, so it will react with NaOH in a 1-to-1 ratio. So NaOH equals to 0.0244295 ... moles. Cool. Now we need to find the concentration. So the concentration is 25 mils. Let me just see if there's anything I need to work out here. Yes. So, if I do 100 mils in that, 25 mils. Okay, so I can't actually jump to there yet because I'm not using the whole solution for titration. Okay, so taking a step back. So I need to first work out the concentration of KHP, which is moles over volume, which is 0.0244295 ... over our volume, which is 0.1. Okay, so let's divide that by 0.1, and we should get 0.244295 ... moles per liter. Okay, now we said it was 1-to-1 ratio between our NaOH molar ratio, NaOH, and our KHP. Then now we can use a shortcut way. Instead of finding the moles, mole ratio, and then moles to over the volume to get concentration, we can do C1V1 equals to C2V2. Now I want to note, this is only allowed to be used where it is 1-to-1 molar ratio, which in other words also applies for dilution as well. Okay, so when you're diluting or you're concentrating, you can use this. Okay, so our C, let's say our 1 is our KHP and our 2 is our NaOH. Okay, so we need to find C2, which means it's 0.244295, and the volume that we used in our titration was only 25 mils. Okay, you see how we couldn't use our moles straight away because we only took 25 mils of the 100 mils. So we do 0.025 over the volume of our NaOH solution, which is the average of this. Now we say this is this is not an aliquot, this is a outlier, and we just do the average of this one. So the average of this is just 27.4. Now, if this is 246, we just choose sort of the middle number, right? So this is difference of 2, so we just choose the middle number. Okay, so 27.4, which is 0.0274. What does that equal? 0.222897233 ... moles per liter. Now we don't need to round this because that's not our final answer. We'll keep this number just to show the markers we're carrying forward this number in full digits. Okay, so this is the concentration of our NaOH solution. Okay, now step 2 dilution, can't work that out until we sort of backtrack and do the back titration there. So we do the titration number 2 with the known mass, known concentration of our NaOH, which is that. Okay, so I need to do this just to have this side by side. Okay, great. What is next? We need to then find the number of moles of NaOH we use in the second titration. So we can say for titration number 2, we have 13 mils, which is, so moles of NaOH equals to 0.0131 liters times the moles of NaOH, which, the concentration of NaOH, which was 0.0222899723 ... moles per liter, which is 0.00291995 ... moles. And we can say the moles of HCl, or not HCl, doing too many HCl questions, citric acid. And now we should note that this citric acid is the diluted citric acid moles, okay, is the same. Oh, is it the same? No, it's not the same, okay? Why is it not the same? Because we haven't written our equation, okay? So let's say citric acid. Again, you don't need to know the equation, but you do need to know that it's triprotic. So if it's triprotic, you would need 3 moles of NaOH to react it with, right? Because you've got 3 H's here, you would also need 3 OH's here to react it as a neutralization reaction. So this would be, instead of that answer, it would be a third, okay? A third. We would need a third of the moles of NaOH because this is a 1 to 3 ratio. Cool? So if we times that by a third, we should get 0.00097331 ... moles. And we can say here 1 to 3 molar ratio with NaOH. Perfect. So we got the moles of the undiluted. Now we can say that for a 25 ml solution of our soft drink, so this is in 25 mils. Again, we can scale it up. If 25 mils has this many moles of citric acid, that means 250 mils has 10 times the citric acid dilution or diluted, which is 0.00973331 ... moles. Now we're nearly there. Now this is the same number of moles that was initially from our 75 ml of the drink. So we've chucked our 75 ml bottle into this 250 ml volumetric flask. So the number of moles is going to still be this. So this would also be equal to the 75 mils of the drink undiluted. Okay, now we're nearly there. Nearly there. Now we've got the moles, then we have the volume. We do have the volume, which is our 75 mils. So therefore, our citric acid concentration, N over V, is equal to that lovely number over 0.075 liters, which is 0.1297757 ... moles per liter. Now, nearly there. We need the units, and we need to round to the nearest to the lowest sig fig that we use. So we use 4.445.4.4.4.4.4.4. So we want to round it to 4 sig figs. So that's 1298 moles per liter, 4 sig fig. Okay, that was a pretty long question, but hey, it's worth the 6 marks there. So again, want to reiterate that we need to clearly identify each step. Just to see what numbers we use for which step, what can we find from each step, what is required to be worked out from each step, and then work it out. Okay, now the other important part that I think a lot of people get confused is the moles and the concentration. Now, just to briefly go over it, the concentration, if you take it out from the same beaker, regardless of how much you take, or if it's the initial concentration, that will be the same. Okay, the moles in 10 mils of the same solution, I have 100 mils of that same solution, okay, as in 10 times 10 of those solutions, not diluting it with 90 mils of water. I'm not diluting it. I'm saying there's 10 times of this specific solution, which is typically done when you take out certain amounts. So this is taken out, 25 mils is taken out from your 250 mils of your volumetric flask. So this 250 mils solution contains 10 times the 25 mils that was titrated, which allows me to make this assumption here, or not assumption, this justification here. This justification here. Okay, you can go around and do C1V1 for 1 step and then do C1V1 for 2 step. You could do that, that's not a problem. I just thought this might have been a better approach. Okay, you'll get to the same answer nevertheless. So that's question 32A. Okay, explain how your answer to part A would be different if carbon dioxide was not removed from your soft drink. Okay, this is a really good one as well, because I do in solution. Okay, so I think as a good starting point is everything is a solution, everything is an equation. So H2O gas in liquid forms an equilibrium to form our carbonic acid. Now our carbonic acid then undergoes another ionization, which gives us our hydrogen ion and then our hydrogen carbonate ion. Why is this important? This guy. What does H plus do in a system? Okay, it lowers the pH, or in other words, it also reacts with our NaOH. Okay, what will happen? It essentially means more moles of H plus, which would require more NaOH to neutralize. Now, how was your answer? The answer we got was the citric acid concentration. So if we need more NaOH to neutralize, that means the calculated concentration will be higher. Therefore, the calculated concentration of our citric acid will be higher, which makes sense because more acid contributes to more of an acid concentration. Okay, 7 minutes. What can we do? Let's do this question. A manufacturer requires this product, has an 85% weight by weight ethanol. Concentration of ethanol in water can be determined by back titration. Ethanol is first oxidized to ethanoic acid using an excess of acidified potassium dichromate. Lovely oxidation reaction. The remaining dichromate ions are reacted with excess iodide ions to produce iodine. The iodine produced is then titrated with sodium thiosulfate. Now, okay, a 25 ml sample of manufacturer's product was diluted with distilled water to 1 liter. A 25 ml aliquot of the diluted solution was added to 20 ml of 0.5 moles per liter acidified potassium dichromate in a conical flask. Potassium iodide 2 grams was added and the solution titrated with 0.9 moles sodium thiosulfate. This was repeated 3 times. The following results were obtained. Great, we've got some titer information. Okay, so essentially it's done all the reaction for us. Okay, so we got reaction 1, we got reaction 2, and we got reaction 3. Alright, so where do we start? It looks like we can't start from the top down because we're trying to find that. We don't have much information about this. Okay, we do have an initial initial concentration of this because we've got volume and we've got concentration. We've got some value of potassium iodide and the solution was titrated with some concentration. So we got the concentration of our sodium thiosulfate. We got the concentration of that. Repeated 3 times. Okay, we got the concentration and we got the volume. So we can do C times V. Okay, let's start with that. So looking at 3, we can say the moles of thiosulfate is equal to C times V, which is 0.9 moles per liter times. Now, we say that's an outlier, and we say the average of that. So let's make a note saying titer 1 is an outlier. Use titer 2 to 4 as average. So the average of that is 28, so 0.0285666 dot 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 liters, which is equal to 0.02571 moles. Yep, and then we got the moles of that. Now we're going to assume that the excess iodide that's produced from equation 2, so iodine, sorry, the excess equation from iodine is the same molar ratio, it's in the molar ratio, okay? So the molar ratio between this and iodine is 2 to 1. So moles of iodine is equal to half of that number, which is 0.012855 moles. Okay, we've already stated the molar ratio, so we don't need to justify that again. Yep, and then we got the excess. Okay, I need to push that down. Okay, great, got that. So, which means it's the excess of this. Now, the iodine to produce, yep, the remaining dichromate ions are reacted with excess iodide ions to produce iodine. So, whatever's produced here is that number. Whatever's produced here came from a limiting reagent of dichromate, because our excess iodide, yeah, our iodides are excess, so that means our dichromate ions are limiting. Okay, so we can say that Cr2O72 minus is limiting. Let's say that's equation 2, as iodide ions are in excess. So we can do a molar ratio again. As you guys can see, there's a lot of molar ratio with acids and base titrations. So hopefully you guys are okay with this, between your chromate, dichromate, and your iodine. So that means our moles of Cr2O72 minus is equal to, sorry, that should be 1, 2, 3, because I wrote it the other way around. Should be a third of that. Which is third times 0.01288, 0.04285. Okay, so that's our moles of our dichromate. Now just going to move over up here. So we're saying that's the dichromate and that's the remaining, right? So we can note that one down. So that's equal to the dichromate ions excess. Okay, now again, similar to what we did earlier, is we want to find the dichromate initial, which is just 0.02 liters times 0.5 moles per liter, which is 0.1 moles. And we do Cr2O7 initial minus Cr2O7 excess to find what's our consumed, because that's what this reaction is happening, right? We want to see what's consumed, and then we can do our molar ratio again to work out the moles of our ethanol. Great, so that's equal to 0.01 minus, that number is 0.004285 moles, which is equal to oops, 0.042850.00571 moles. Now we've got the moles of our consumed Cr2O7 minus 2, and then we do moles of C2H5OH over moles of Cr2O7 2 minus consumed. That molar ratio is 3 to 2, so that means our moles of our C2H5OH is equal to 3 on 2 times our moles of our dichromate consumed. And then what does that equal? 0.0085725 moles. Now what is the question asking? Does this sample meet the manufacturer's requirement? So we've got moles, we've got an 85% volume by volume, we have a density. Okay, so that might look like we want to find the mass of C2H5OH, which is the molar, the moles times the molar mass, which is this. Molar mass is 2 times 12.01, 6 times 1.008 plus 16, which is 12.01 times 2 plus 16 plus 6 times, 6 times 1.001, which is 0.3949174. That grams, and then we want to convert that to volume, which is this grams divided by 0.789. Sorry, that should be, that's a typo. 9 grams per cubic centimeter. Now cubic centimeter is also milliliters. Okay. Something is wrong because I am not getting the right answer, or answer, because that is huge. So what happened there? Ah, I see my typo. It started from the very beginning. Oh no, did it? 0.9 moles per liter, 2 to 1. Two to 1, which means that. Let's backtrack and try to work this out. So 24.8, 24.4, 28.6 divided by 3. Yep, that's the right volume. That should be the right moles. Is equal to 2 to 1. So our moles of that should be half of that. Yep, half of that is correct. Limiting 1 to 3. 1 to 3. Let's write that out again here. One, 2, 3. So that means, this is where we went wrong. This should be a 3. It's very important we look. Oh no, it's not. It's not. This is a third of that. 0.04. That's excess. Moles. 0.01 moles. That's that. Consumed. Is that? Is that 16, 24, 40? Is that the right number? 0.08. 0.39. Strange. What did I do previously? So this is my working out previously for the question. Oh, that's a KHP. So did I just type in a calculator, incorrect calculator value? Because I got that 0.428. Yeah, I got that. Then I got that. Yep. Ah, is it my ratio wrong? No, I got that. So then what's wrong then? Ah, again, we missed the step of dilution. Very good. Okay, so very good. So it's caught us out again. So this is the moles of the diluted. So what do we need to do? So yes, of the diluted. So this is the moles of the diluted ethanol. So we can say that if there is 25 mils of the aliquot solution is this, it was originally diluted into this, 25 mils aliquot of a dilute solution was added to 20 mils of that. So this is the moles of 20 mils. So if we say in 25 moles of C2H5OH is equal to that, then in 1 liter, N of C2H5OH is equal to 40 times of this. Because we are raising that volume, and what is that volume? What is that moles equal to? 0.3429 moles. Yep. Now we can find the mass. Let's find the mass. 0.3429 times 12.01 times 2, 6 times 1.008 plus 16. Let's see what we get. 6 times 16, which is 15.796 grams. Now we want to convert that to mils. And we want to divide by that to get milliliters, which is 20.02118783 milliliters, and we had 25 mils, so the percentage weight per volume is 20.02118783 over 25 mils. And we're going to times that by 100%. That's a very ugly 100%. Which is 80.0847 which is less than 85%. So therefore, does not meet the requirements. Cool. All right, great. Sorry, I went a bit over time today, but there's a couple of more questions that needs to be done. I will post the solutions up of these for you guys to reference, and hopefully you guys learnt a little bit about this one. Okay, any questions, guys, please let me know in the comments below. All right, thanks guys, have a good night. Good luck studying.